Hello everyone, my name is Selva Calixto. I'm the founder and CEO of Sustainable Heating. We specialize in helping building managers, utilities, and large-scale developments decarbonize and enhance energy efficiency through planning of heating and cooling systems. The presentation of today is focused on decarbonization strategies for New York City buildings. The purpose of the presentation is to provide you with a practical and career-relevant skill in LL97 carbon modeling. We will see what is LL97 shortly. Electrification and decarbonization strategies, evaluating retrofit options and penalties. The first 5 minutes I will introduce you on LL97 and provide you career context, and in the following 20 minutes I will show you a case study using the LL97 calculator. So first of all, why this is relevant for you? If you work in New York City in sustainability, LL97 compliance is central to the city goals. And employers value candidates who understand carbon policy and emissions modeling. So knowing decarbonization is an opportunity for not only engineering backgrounds, but also for policy and construction roles. So first of all, what is Local Law 97? It is a law that applies to large buildings larger than 25,000 square feet. It sets annual carbon emission caps starting in 2024. And buildings that do not comply with the law, the penalties are $268 per metric ton of CO2 if you go over the cap per period of time. It tightens over time, so starting 2030 and onwards, 2035, 2040, it gets stricter and stricter, therefore requiring proactive planning. So today I will show you a case study where a typical building located on the Upper East Side of New York City that consists of a mid-sized multifamily residential building with a ground floor with retail space is selected. We're going to imagine that this building has three main energy sources: electricity, and for heating you have two kinds of sources: natural gas and fuel oil. We're going to use the LL97 calculator, which is an important tool relevant for you if you want to pursue a career in sustainability in the city. This tool is right here. If you click on the link, I'll show you now. You can access to the tool. It allows you to develop several scenarios for decarbonization strategies. You close this disclaimer. And how does it work? On the left hand side you have a panel where you can input certain values that allow you to develop a certain scenario. So for this case study we are going to select from this drop down menu the kind of building that we're going to work today, in this case a multifamily housing building with the ground floor, a retail space, a retail store with a certain specific number of square feet. So you can input manually here the values. And maybe I'll show you in the next slide. I have here the values we're going to use for this case study. As you see here, I need to input these values for the area of the building and the use of the space, and also the specific utility inputs for electricity, natural gas, and fuel oil. And also I'll show you what kind of simulations can you do using this tool. Let's go back to the tool. You can either input the values manually on this panel on the left-hand side, or you can simply find a building using this function. So here you can input, for example, any address in New York City, and it should allow you to load the data for a specific building. So as you see here on the left-hand side, if the building is within the database, it automatically fills up all the information from that particular building. And not only this, the tool immediately calculates what are the emissions this building has for different periods of time. That is in the first row. The second row tells you the threshold in tons of CO2 emissions per year, that according to the LL97, the building needs to comply at its maximum, and an estimated value of the penalty in dollars per year. As you see, with time, it gets much more strict, and therefore the penalty grows. If you want to see a more detailed analysis on what is contributing to these emissions, you can do so by clicking End Uses. So here it shows you where the emissions come from. In purple, you see fuel oil number 2 as the main energy source for carbon emissions, then electricity, and finally gas. On this tab, Cost, you can also see a breakdown of specific energy cost or utility cost, and also the estimated penalty, as well as an estimation of the total cost for this building in total, including energy cost and the penalty cost. So for the exercise of today, I have already input these values here as it is shown on the table, and we will do two things. On the one hand, analyze what happens if this building doesn't do anything. So this is the business as usual case. As it is shown in this graph, the building can faces at least $27,000 per year if they don't comply with the law, with the current situation. And the cost of operational cost of running this building, also if nothing is changed, is about $282,000 per year. So in the presentation here, I have you can verify, you can do yourself also with these values. The estimated penalty for the first period is about $27,800 per year, and the total annual cost for the first period also before 2030 is about $28,000 per year. So the question that now we are going to analyze is what can happen if certain retrofit measures are in place to cut emissions and avoid fines. So here we have 4 scenarios. The first scenario is the energy efficiency, in which one can focus only on upgrading lighting systems with a consequence of reducing electricity use by just 10%. The second scenario is switching the fuel used for heating, instead of using fuel oil, to natural gas. The third scenario will be not only upgrading the lighting systems, but also optimizing the heating and domestic hot water systems. And as a result, we get a reduce in gas and oil use by 20%. And the final scenario is the deep energy retrofit, in which we combine all three previous strategies and we electrify the building 100%. Then we will compare how does the retrofit affect the penalty for the first period from 2024 to 2029. Does this eliminate the penalty entirely? And most importantly, which of these strategies eliminates penalties in the long term? Alright, so what are the results of scenario 1? If we focus on just lighting efficiency, as you see, the penalty is reduced very little the first period from 2024 to 2029. So what would be the percentage of electricity that should be reduced in order to completely avoid this penalty? It's a 45% reduction, which eliminates the penalty for the calendar years 2024 to 2029. The question here is this technically possible? Probably very, very challenging. So which are the other options? Scenario 2. Let's imagine that we don't do any kind of energy efficiency measures. We just switch the boiler from oil to natural gas. As we see here in the results of this graph, penalties for the first period are reduced almost completely. But is it a long-term strategy? We see here that starting 2030, the penalties are still very, very high, with $47,000 per year. So converting from fuel oil to natural gas significantly reduces carbon emissions, but it's not a long-term strategy. Why, you ask? As you see here in this graph, the main contributors to CO2 emissions are gas, mostly, from combustion of the fuel. What happens if we focus on electricity energy efficiency measures and we focus also on heating efficiency? The first period, 2024 to 2029, reduces in 100% the penalty, but the same case happens scenario 3 with scenario 2. It is not a long-term solution because you are not solving the main problem, which is the use of fossil fuels for combustion. So in this case, fuel oil number 2 is also contributing mostly to the carbon emissions for this building. In scenario 4, and before I go deep into the analysis of this graph, I want to show you a spreadsheet I generated in order to get these results, and is in here. So all the details of the calculations, you can find it in this spreadsheet. I will share it with you at the end of this workshop. So for this case, I applied a certain methodology, which is explained in this spreadsheet. The first step that we are going to assume is that the existing electricity consumption used for lighting, plug loads, and AC can be optimized through low-cost energy efficiency measures to achieve a 20% reduction in consumption. So the next step we are going to assume is that we reduce the actual heating required by the building through improvements like air sealing, insulation, and window upgrades. This immediately has an impact in the use of both fuel oil number 2 and natural gas. And the third step is electrification with a heat pump. So the last step is to convert completely the fossil fuel systems. We remove them and we replace it with a high efficiency electric heat pump system. So after some conversion factors from the the fossil fuels used to electricity, we get a total amount of electricity used in this building of about 1 million kilowatt hours. So this building is now 100% electric, eliminating all on-site combustion and achieving a final total electricity consumption of about 1 million kilowatt hours. So coming back to the presentation, what will happen if this is the case? We see a reduction in the penalties. So you don't have any penalties until 2049. Still, in after 2050, you get a certain penalty of about $40,000 per year. And this shows that basically the calculator is assuming a certain amount of CO2 emissions associated with electricity. But in case by 2050 the electricity grid is 100% renewables, then maybe this factor is reduced and therefore the penalties can be reduced. So in summary, we have learned in this very basic mathematical exercise that a substantial 45% reduction in non-heating electricity may achieve a short-term compliance, but it requires deep retrofits and does not address the highest emitting systems, which are oil and gas heating. Also, we learned that converting the high carbon fuel oil number 2 to natural gas lowers the LL97 emissions factor for short-term compliance, but is not viable long-term strategy because the caps after 2030 are significantly lower and will require further transition. And finally, converting to 100% electric building in the best case scenario that can be probably consume a bit more than 1 million kilowatt hours, eliminates all on-site combustion and provides the highest regulatory certainty, effectively exempting the building from LL97 penalties until 2049. The key takeaways for this exercise is that LL97 penalties drive demand for decarbonization solutions. Knowing how to use a modeling tool like the one we saw today is a valuable technical skill if you want to work in sustainability, in buildings, in your city. We learned that energy efficiency plus electrification is the fastest path to compliance, and this mathematical exercise is a real-world preview of professional building modeling tasks. Here you can find some useful links. The first one is the spreadsheet that I just showed you if you want to dive deep into the details of this exercise, and also useful links for training opportunities in this sector. Thank you for your attention, and if you have any questions, please let me know, or you can reach me out by email or LinkedIn.